Okay, Bismillah Rahman Rahim. We already discussed the posets, and now today we're going to discuss about lattices. And when we say posets, it's a combination of set S and relation R on that set S, which is basically an partially ordered relation, wherein we say that what we say is that the R is reflexive, antisymmetric, and transitive. We know that. Now today we want to learn about lattices. Before that, we would like to learn about a few things like lower bounds. So what is a lower bound exactly? So if we say that we have a comma b, which is basically the subset, or it's less than or equal to a, b, and c, right? Then we say ab is a lower bound of this. But if we have a set of things like we have the subset of any set, if it is a poset, for example, on a set A, if we have a poset on how should I make it, sorry, like this, the poset on a set A, okay, poset of set A, and we have S as a subset of this, right? Then if we have the situation if and only if, okay, for example, let me define it like this, that the definition what I'm talking about, and the element of the poset on set A, X is a lower bound. I see something as an X as a lower bound of a subset of prime and S if and only if for every element, for every y, say for example, which belongs to the S, X is subset or equal to Y. That means if I am talking about any X which I want to say is this a lower bound or not, then if we have other elements which like Y which belong to this S subset, which is the subset of the set A, then X should be involved, or it should be subset or equal to each and every element Y which belongs to the S. For example, if I am having a subset, if I'm having a subset of a set A, like A comma B and B comma C, now this is my subsets, for example, then if I take A, for example, A, this cannot be the lower bound because this belongs to this, so Y here are all these elements, ये सब elements Y है और ये आपका X है. क्या ये इसका lower bound है? नहीं, because A is in here, not here. If I talk of B is in both, so B is also a lower bound, right? If I talk of BC is only here, so this is not a lower bound, right? So in this case only the set B is a lower bound because it belongs to AB as well as BC. You getting me or not? So we could have also the multiple lower bounds. For example, if I'm having a subset which I was talking of, S is equaled, say A comma B comma C and B comma C, right? Then what are the lower bounds? The B can be lower bound because in both sets. The C can be lower bound, it is found in the both sets. We can have a BC, again a lower bound in both sets. We can have should we have an ABC? No, or an OI or null set. They are all lower bounds. Now among these lower bounds, if I talk of BC, this is called as the greatest lower bound. So what is a greatest lower bound? A greatest lower bound is something which should be the lower bound, means it is the lower bound of the set S, for example, and among the lower bounds all other lower bounds should be subset of this. That means if I talk of B, C and null set here, all the three are subsets of this lower bound. So BC is a lower bound, but it is a greatest lower bound. You getting me? So we say it like this: A is equal to greatest lower bound of set S. So when is it possible that A is a greatest lower bound? So how can I say that A is a greatest lower bound? So what is the definition of greatest lower bound? So if we define the greatest lower bound, I say an element. Should I pause it and write it? So what we are talking about is an element A is the greatest lower bound. If we talk of some element A, which is the greatest lower bound of a set, so we say that GLB of S, right? It's a GLB of S if and only if we have these two conditions satisfied. First, that A should be the lower bound of S. It should belong among the lower bounds. The lower bound is something which is subset of every other set in a sets which belong to the S, right? For every lower, we have already done that, and also now we found the lower bounds. Then for every lower bound B of S, now if we have other lower bounds also, say B, then B, those all other B's which are also the lower bound of S, and A is also the lower bound of S, and A is a greatest lower bound if B is a less than or equal to A, or B is a subset or equal to A in other sense. In this case, we write A is a GLB of S, that it is the what is called as greatest lower bound of S. You getting me? Okay. For example, we've already seen here that ABC and BC, this is my S, which is a subset of the set A. Okay, then we said that B, C, BC and null set, these are the subsets. Basically, these are the lower bounds of the set S. And among them, BC is the greatest lower bound because all other, lower bounds are basically the subset of BC, or this set, this particular set. So this is the GLB, greatest lower bound of set S. Now in general, when we have two sets or three sets or whatever, if we have two sets, for example, okay, for example we have here B and C, these are our two sets. If I want to find greatest lower bound of the sets, for example these two sets, sorry, if I'm talking of these two sets, not these two sets, because if we talk of these two sets of which we have to find the GLB, greatest lower bound. So we want to find the greatest lower bound of this set ABC and BC. What we believe GLB is basically the intersection of these two. So what is the intersection? That is in fact the BC, right? So the intersection will come up as your greatest lower bound. So we can add up this information here that in general, so we say point number third, in general, when A comma B are sets, then GLB of A comma B will be equal to what? A intersection B, right? What is the intersection of A and B? Just get that together. That will be our GLB. So the next thing, we have got the GLB. Now the next thing is the least upper bound. We deals the upper bound. The upper bound, to understand upper bound is very easy now. Among the upper bound, we need some least upper bound. Okay. I will write a definition here. So what we're talking about is an element A. If you want to say, is my element A least upper bound or not, right? Of a set S, so LUB of S is the least upper bound of set S, the element A, if it satisfies these two conditions, that A should be the upper bound of S, and also that every upper bound B of S, now we have other upper bounds B of S, then A should be the subset equal to B. It is if you see the previous one, then the B's should be less than or equal to A. Here we have A is less than or equal to B in the lower bounds. Now in upper bounds, we say A is less than or equal to B, so it should be upper bound and it should be the least. Simple thing, right? So now you must have a question: what is upper bound, what is least? What is the least upper bound? And then so let's do an example to understand it. Let's do it with an example, right? Okay. So here we go with our example. Let me change my pen. Say for example, we have a poset, okay, on a set A, and that is A, B, C is my set. So what will be the upper bound first? S. All upper bounds. Upper bounds will be A, B, I mean if we have the subsets A and B of the poset ABC, so what are the upper bounds of S? Now these are the upper bounds will be, what do you think upper bounds will be? Upper bounds will be AB, okay, then it will be A, B and C, because we have A an upper bound if our each element in a set S should be the subset of this. That is the upper bound. Now if I talk of AB, now these two guys are subset of this. If I talk ABC, these both of these two guys are the subset of this. So these two are the upper bounds then, and we do not have other than these elements here in my main set, right? So we have two upper bounds now, AB and ABC. Now definitely if you could see, AB is the least upper bound. Why? Because according to our definition, if we are saying that A is an upper bound of S, so yes, we say that this AB is an upper bound of S, okay, for every upper bound of B of S. Now if we have other upper bounds, like we have the one upper bound here, right, this guy is another upper bound, then what you are talking about should be the subset of that. It should be least among the upper bounds, so it will be automatically subset of all other guys which are upper bounds, right? So simple thing is that it should be upper bound and should be least among those, so that's called least upper bounds. Now these all things are required if we talk of lattice. Then we have an operation that's called meet, shown by the symbol like this. Usually we show this as an and operation in a discrete mathematics, and it is an operation on a greatest lower bound. So it is a, what is a meet? It is a greatest lower bound operation. It is an operation on greatest lower bound, right? So if you have two elements, consider two elements, we say P and Q of a poset, we define P meet Q, it's read as P meet Q, right, is similar to GLB of P comma Q. So whatever is the greatest lower bound of P comma Q, right, that will give us P meet Q. If you want to go for P meet Q, we have two sets, say P and Q, we have two sets. I'm going to find the P meet Q, then basically we have to find what is the GLB, greatest lower bound. And if you remember, I said if we have two sets as GLB, it will be intersection of those. So you got to do the intersection to get it. Okay, so P, this thing is read as how is P and Q read as? This P meet Q is basically read as P meet Q, not P and Q, right? Similarly, another operation, what's called as a join, shown by the OR, right? So at least it is a least upper bound operation. We have a greatest lower bound and the least upper bounds. It should be upper bound and the least among them. The lower bound and the greatest among them is called GLB, right? So if we have the join operation, similarly we have considered two elements, P and Q of a poset, we define. Similarly, if we write same thing there, it is similar to saying that least upper bound of P comma Q, right? Find the LUB of P comma Q, you will get what will be the P or Q. How we get the, if in this example, if we say how we get the least upper bound of the two sets, if we got A and B. So definitely in the previous case we had an intersection, in this case we have basically the union, right? The minimum thing will be the union of these. It starts from the union, then it will start from the union of this with this, right? If you want to get the upper bounds, basically you have to do first union of these two guys, then start doing union of the parent set, right? You will get all the upper bounds. And basically if you got the least upper bound, that will be the least thing is to do the union of these two. Union, so what will be it? It will be, if you have two sets P and Q, then what will be the greatest lower bound of P comma Q? That is basically equal to P union Q. Remember that thing also. So if the shortcut to get out the GLB. Okay. So if we want to say P join Q, so it should be least upper bound P comma Q. How we get the least upper bound of P comma Q? Just union them and you will get the join operation. Yes, right or not? Getting me? So now comes the time to discuss the lattices. So lattice posets, because lattice is nothing but a posets but having certain characteristics, right? So what is a definition of a lattice poset? So a lattice is a poset. First thing is that lattice is a poset, okay, A, in which if you say it is a lattice, the poset A, in which for every P and Q, if we have the subsets like P, we have Q which belongs to the A, then P meet Q should belong to A, or this implies to the GLB of P comma Q should belong to A. So if you are given some set A and you say that is this a lattice or not, if it is a poset A, first it should be a poset. Second, we will see that P comma Q, if we have two sets, then P and Q belong to A, then P meet Q, is it belong to A or not? How you get a P meet Q? You will find the GLB of P comma Q and that should be in a A. If it belongs to that, then it may be the lattice, but we cannot say it is, because we have to go for another operation, that is P join Q. So is P join belonging to A or not, right? If it is also there, it should be there, which is actually the, how we find that is the least upper bound of P comma Q. It should also belong to A. If both of these guys belongs to A, then we can say the particular poset is a lattice. You got me? So how can you say that if you want to represent this, we can say that this is basically that we should have a set A, okay, and on that we should have the what's called as the meet and join operations. You getting me or not? So let us give some example to understand it. Now consider, for example, we have some set which is a power set, basically a power set. We say something is a power set, that P is a power set of set S, right? And we have a relation subset equal. This is a poset, we know, but is this a lattice or not? This is lattice only if these two guys are belong to this S. Now definitely if we say P meet Q, this is actually the GLB, greatest lower bound, and if we say P join Q, that is basically the least upper bound. So least upper bound, I get the least upper bound by the union. If we have the power set, for example, and we do the union of the two sets, that will definitely be in the power set, right? Similarly, how get the GLB? GLB we get, if we have two sets P and Q which belongs to the set S, then that will come up by the, that is the join operation, meet operation, that will come up by the intersection. So definitely that intersection P intersection Q will definitely belong to this power set, because power set has everything in it. So then this is definitely a lattice. So you have to show in terms of this, right? You have to show in terms of, get some example, make some, say for power set of something, make the power set of something, and then show that P meet Q and P join Q are there. So therefore it is a lattice. So we discussed a lot of things today. One was the lower bound, then we set the greatest lower bound, then you have to understand what's the upper bound and what is the least upper bound, so unions, intersections and all. Then we got some meet operation, and we got some the join operation, and if both of these guys are in a set A, then we can say that that poset on a set A is a lattice. So we have to find if the GLB and LUB is there or not, so then it simply is a lattice. Getting me? That's all for this segment.